Okay, so as always, now that the recording is on, you can type your name into the chat so that we have a record of your attendance. It's good to see everybody this week. I hope you're all doing fine. Um, yeah, so I want to kind of finish this. You basically this week and our next session will finish a lot of our main unit on differential calculus, and we'll spend the rest of the class talking about some other things. But yeah, today's going to be a pretty important class because we're going to learn the chain rule, which is one of the last rules for taking derivatives, and we're going to show an application that's a pretty versatile application. So we've already seen applications to maximizing and minimizing things. And this week, we're going to see an application to something called related rates, which is asking about how when you have a bunch of different quantities that are related to each other, and you know the rate of change of one of the quantities, then how can you figure out the rate of the change of all of the other quantities? Okay, so that's going to be kind of the two main topics that we're going to cover today. But before that, we'll go over everything that we've been doing with this geometry of what it means to take the first derivative and what it means to take the second derivative and how that's reflected in the graphs of functions. So we'll review that with the homework questions, and then the rest of today will be a little bit more computational, a little bit less about graphs and a little bit more about computations. Okay, so again, thank you as always for continuing to attend. And I will and remind you just once again, if you haven't written your name in for the attendance, to write it down so that we can make sure that you are able to keep getting the data that you deserve. Okay, great. So let me just recall this main thing that we've been talking about over really the last month, which is this geometric meaning of the first and second derivatives, right? So what we've used a lot is that if you have a function f of x, then if the first derivative is positive on an interval, if f prime of x is positive, then that means that f of x is increasing on that interval. And similarly, if f prime is negative on an interval, then this is a typo here. This should say just f of x, not f prime of x. Say f of x is decreasing on that interval. Give me 1 second. I'm actually going to put in headphones. Let me do this just because there's a bunch of other people around. So let me put in my headphones. Okay. So So this is the geometric meaning of the first derivative, and we've spent a lot of time talking about this. If it's positive, that means the slope of the tangent line is positive, and that means the function is increasing. And if it's negative, that means the slope of the tangent line is negative, and that means the function is decreasing. Okay, so we also saw that the second derivative has a meaning. So if the second derivative is positive on an interval, then the graph of the function is concave up on that interval. And if it's negative on an interval, then the graph of the function is concave down on that interval. And then lastly, we had a definition that if we have a point c comma f of c on a curve whose the graph of y equals f of x, that this point is called an inflection point if, well, the function has to be continuous there. And then the key thing is inflection means that the graph goes from being concave down to concave up, or from concave up to concave down at that point. And we saw last time that if you have an inflection point where the second derivative exists, then the second derivative has to be equal to zero. So usually we just we just find inflection points by setting f double prime of x equals zero. As long as all the derivatives exist, then this is going to be the only place where you're going to find inflection points. Okay. So Okay, so this is the meaning of the first derivative, tells you whether it's increasing or decreasing, and then we have the meaning of the second derivative, which tells you whether it's concave up or concave down. Okay, so this is all review of things that we've talked about over the last couple of weeks, and let's just put this to use. So for the homework exercise one, we had a graph, and the first question was just to find where are the inflection points. So let me redraw this graph for you here. So the graph looks like this. So this is 0. I'm going to label 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Sorry again. Please keep yourself muted unless you're asking a question or answering a question. Okay, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. All right. So let me draw the graph for you. So it's going to look like this. Okay, so this is going to be the graph of some function y equals f of x. Okay. And the question is, so for the first question, we want to know just where are the inflection points. So we want to see basically from looking at this graph, where does it go from concave up to concave down, and where does it go from concave down to concave up? Any place where one of these things happens is going to be an inflection point. And I think instead of writing down the numbers of where they are, I think we can just go ahead and label the inflection points on the graph, right? So we're just going to label the inflection points in red. So does anybody want to tell me where, one of the inflection points is? Or, it's a bit of a matter of judgment because I didn't draw the graph perfectly. You have to just kind of eyeball it and see where you think the concavity of the graph changes. Does anybody want to say where they think one inflection point is? Okay, well, I'll start us off, right? So it looks like over here, as we follow the graph along, this part is concave up, right? It's kind of holding water here. Maybe I'll color code this, right? This over here, it looks like it's basically concave up. And then this part over here looks like it's spilling water. So between 2 and 4, this looks like it's concave down. So maybe I'll label the inflection points in green. Here we have a transition from concave up to concave down. This should be at that green point over there. So at x equals 2. Okay. So that's our first inflection point, right? And now where does it go? We have kind of concave down, concave down, concave down, concave down. And then here it starts changing to concave up, right? Because it goes from spilling water to holding water. So where is it going to be concave up? It looks like it's concave up basically over this next interval. Concave up. And so that means that you're going to have an inflection point in between where it's concave down and concave up. That would be here. Okay. And then, well, what do we have? We have concave. It looks like it switches again to concave down over here, and it stays concave down, I don't know, till a little bit after x equals 7, right? So maybe I'll call it here to a little bit after x equals 7. This is going to be concave down. And we'll again have an inflection point where it changes. It'll be a little bit after x equals 7. And also we have an inflection point over here where it changes from concave up to concave down. And then for the rest of the graph here, it basically looks like it's concave up, right? So I'd say the rest of the way, it looks like it's concave up on the entire graph, so there's not any more inflection points. So the green points here should be the inflection points. Okay, and you get this, you don't have to do any equation solving to do this. You just get this by looking at the graph. You're seeing where the concavity changes from concave up to concave down, back to concave up, concave down, and then to concave up. Okay. So this is this is one this is a way that you can find these inflection points. And there's not really any other way because I didn't
Yeah.
give you the equation. So there's nothing else that you can really do. Yes, question?
Okay. Yeah. I thought you were
Yes.
asking. asking her to, yeah, to find a, if
Sorry, I was getting you, but not anymore. You went out.
I thought you were asking her for to find a reflection for this point. For me, I want. Oh, okay, okay, okay.
Okay.
Are you getting me, sir?
Now I'm getting you. Yes.
Okay. I said I thought you were asking us to find a reflection point for the concave up and concave down. So can
Right.
we identify the point to be two and four for concave up and down or concave down? Two and
Yeah,
four, which is six.
Yeah, usually we don't categorize inflection points. Like, so an inflection point is anytime you go from concave up to concave down or from concave down to concave up. So if you want to say concave up to concave down, sure, that happens at 2 and 6, and concave down to concave up happens at 4 and, a little bit after 7. So if you want to break them into those two families, you can. But the question didn't really ask for that. It just asked for all of the inflection points. So an inflection point is any time you've got any change between concave up and concave down or concave down to concave up. It doesn't matter which direction the change is. So all the question really needs you to do is find all of the inflection points. Okay.
Okay, sir. Okay.
All right. Great. Thanks. Yeah. Right. So approximately 2, 4, 6, and 7.5 as James writes. Yeah. So that's good. Okay. Great. Okay. Great. Okay. Any other question? Okay.
Yeah, I have a question.
Yes. Rush.
Yeah, joining the class now, you're talking about the reflection
Okay.
point. So I can elaborate.
Yeah. So sorry. What's the question?
I just want to know anyway about the reflection point you're explaining, but I'm not getting it clear first.
Oh, okay, sorry. So what is an inflection point? So right. So on the previous slide we had an inflection point here is when the graph goes from being concave down to concave up or from being concave up to concave down. So it's whenever you make a change from one kind of concavity to the other kind of concavity. And so and it also, the function has to be continuous there. So when you look at the graph, what we see is we're going every time we're making the transition from concave up to concave down to concave up to concave down and then back to concave up. Every time that changes, that's an inflection point.
Okay, okay. Thank you, thank you.
You're welcome. Okay, so let's look at exercise 2, which is a little bit harder. So I'm going to draw the same graph. I'm going to draw it again over here. So let me 1, 2, 3, 4, 5, 6, 7, 8, 9. And let me just redraw this so it's like goes down here and then up here and down here. And then at 6 it goes up and a little bit over like that and then up. Okay, so let's say this is our same graph. But now, so this is the question's meant to be a little confusing. So imagine that this is the graph of y equals f prime of x. So that means f of x is some function and this is the graph of the derivative. Okay, so that's the setup here. So we have some function, but I'm not giving you the graph of y equals f of x. What I'm giving you is the graph of y equals f prime of x, of the derivative of f. Okay? And so now it looks like we have, 6 different questions here. But let's just look at the first one. So we want to know, where are the inflection points of f? So remember, where the inflection points of f are, by the definition of inflection point, is what? It's where f goes from concave up to concave down, or where it goes from concave down to concave up. So let me just see, like, if we want inflection points. Okay, well, this is f goes from concave up to concave down, or concave down to concave up. Okay, so this is the meaning of an inflection point. F goes concave up to concave down or concave down to concave up. But what we're given here is um, is the graph of f prime, right? So let me say also, what does this mean? Concave up to concave down means f double prime of x is greater than 0 goes to f double prime of x is less than 0. And concave down to concave up means f double prime of x is less than 0 goes to f double prime of x is greater than 0. Right? So these are what these transitions are. So we have to detect this by only looking at the graph of f prime. So by looking at the graph of y equals f prime of x, we want to know, for instance, when is f double prime of x greater than 0, and when is f double prime of x less than 0. And if we can figure that out, then we'll know how to find the inflection points. So, the key thing to keep in mind to observe is that f double prime of x is equal to f prime of x prime, right? I mean, to take two derivatives means you have the one derivative, that graph is already drawn here, and then you're taking another derivative, right? So f double prime of x is greater than 0 when f prime of x, well, when the derivative of f prime of x is greater than 0, and that means when f prime of x is increasing. And f double prime of x is less than 0 when f prime of x is decreasing. Okay, so this is a key point. Before we actually answer the question, I want to make sure that everybody understands why this is true. The second derivative being positive or negative is the same as the first derivative being increasing or decreasing. Because when the first derivative is increasing, that means that its derivative is positive. That's the second derivative. When the first derivative is decreasing, that means that its derivative is negative. Yeah. Okay. So does this make sense before we go on and answer the question? Okay. If this is okay, then, well, we have to see. So what are the inflection points? Well, we look to see where this goes from decreasing to increasing. And that's exactly going to be at these kind of local minima and maxima. So I'm going to go label all these points where it goes from decreasing to increasing like this, right? Because here it's decreasing, then increasing, then decreasing, then increasing, then decreasing, and then increasing. So all of the points that I've labeled in green, the green points are inflection points of f of x, because it's exactly the points where f prime changes from increasing to decreasing. Okay. So similarly, I can try to label the critical points of f. Maybe I'll do this in purple. So this is going to be the critical points of f. Right, so remember, a critical point of f is exactly when the derivative of f is 0. And so since this graph shows the derivative of f, we just have to check where it's equal to 0. So any point where f prime is equal to 0, so that's exactly where it passes through the axis, these purple points here are going to be the critical points of f, because they're the points where f prime is equal to 0. So it's passing through the x-axis. F prime is passing through the x-axis. That's what makes it a critical point of f. It's a little confusing, right? Because the inflection points of f are actually the critical points of f prime. They're related to each other that way. Okay. Questions so far? Okay, and now the other questions we've basically figured out already, right? We want to know, where is f increasing? Well, it's increasing. We've seen exactly where f prime is positive. So we can have, so f is increasing. So f of x is increasing exactly when f prime of x is positive. So we know that f is increasing when f prime is positive. And since this is the graph of f prime, we can just see where it's positive. It's positive between 2 and 4, and it's positive when x is greater than 6. So this is between 2 and 4 and between 6 and infinity, right? Yes, you can name the critical points and the inflection points numerically if you want. Yes, you could call that you have critical points at x equals 0, x equals 2, x equals 4, and x equals 6. And you have inflection points at x equals 1, x equals 3, x equals 5, x equals 7, and x equals 8. Just to save space, I decided to just label them here so we wouldn't have to write them down. Okay, and so similar, f of x is decreasing when f prime of x is negative. And so this is, when is it decreasing? Well, this is exactly when f prime of x is negative. So we see that's between 0 and 2 and between 4 and 6. So this is on 0 to 2 and 4 to 6. These are, of course, intervals, not points. Okay. And last we want to know, where is f concave up and where is it concave down? Well, we already know that concave up corresponds to f double prime of x being greater than 0. So it's concave up exactly when f prime is increasing. And similarly, it's concave down exactly when f prime is decreasing. So we can look, maybe I don't have a great amount of space to write it, so I'll just tell you, and then I'll write it on the next sheet for the just for your records. So the f prime of x is decreasing between 0 and 1, and between 3 and 5, and between 7 and 8. Whereas f prime of x is increasing between 1 and 3, and between 5 and 7, and between 8 and infinity. So these places where it's increasing and decreasing are exactly where the second derivative is positive and negative, and that means the function's going to be concave up or concave down. So I'm just going to add an extra sheet where I write this. So f of x is concave up for x in, so we have 1 to 3 and 5 to 7 and 8 to infinity. So 1 to 3, 5 to 7, and 8 to infinity. And f of x is concave down for x in basically everywhere else. So that's going to end up being 0 to 1. Over here, that's 0 to 1, and 3 to 5, and 7 to 8. 1, 3 to 5, and 7 to 8. Okay? All right, so the point of this exercise is that it's asking you a lot of questions about properties of f, whether it's increasing or decreasing, concave up, concave down. All of these things have to do with derivatives of f, the first derivative and the second derivative. But you have to detect that information not from seeing the graph of f, but you have to detect it from seeing the graph of f prime. So in a couple of weeks, we'll actually put this in a practical situation. If you want to think about f as a position function and f prime as a speed function, if you only know the speed or the velocity that an object has at certain points, what can you detect about its actual motion, about its actual position at those points? So we'll see this, in context of speed and acceleration and position. Okay, so we won't do that today, but we'll see that in a few weeks. Okay, any questions about this exercise? So by the way, Miata, just one thing for your comment. 8 is also an inflection point. It's not a critical point. So this 8 here is should be on the first list of inflection points, not on the list of critical points. And that's because 8 is a critical point for f prime, which means it's an inflection point for f. Okay, so it's a point where the derivative goes from increasing to decreasing. So 8 is with the greens, not with the purples. Okay. 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 So let's start a completely new topic. So if you want to follow along in the textbook here, this all is section 2.5. Okay, in the textbook. So this is called the chain rule. Okay. So let's say that we have two functions, f of x and g of x. So we talked earlier on this year about how we can compose these functions. So you can do f of g of x, which means you apply one function first and then you apply the next function. Okay, and sometimes as notation, this is written f following g. And so as an example, let's say that f of x is x squared and g of x is sine x. Then if you take f of g of x, that means you do g of x, you first do sine x, and then you do f of x, which is squared. So you do sine x and then you square it. So that's sine x squared, or sometimes that's written sine squared of x. But we've also seen that if you reverse the order of the functions, if you write g of f of x, that means you do f of x first. So you start with x squared, and then you apply g. Then you apply sine. And you end up getting sine of x squared. And we see that sine squared of x and sine of x squared are just different functions. And you can try plugging in your favorite value. You're just going to get different results for them. Okay? So sine squared of x and sine of x squared are different functions. And so when you compose, it matters what order you compose in. And so one of the things that we're going to want to do is we're going to want to figure out how do we compute the derivative of a composite function. Okay, so we've had rules for how you do derivatives of polynomials and trig functions and adding and subtracting functions and multiplying functions and dividing functions. So, all of these ways we have rules for the derivative. But for a composite function, we don't have a rule for the derivative yet. Okay, so we're going to make a rule, and that rule is going to be called the chain rule. So this is what we're going to talk about. So the chain rule is going to tell us if you have a function f of g of x, and you know the derivatives of the individual pieces, so you know the derivative of f, and you know the derivative of g, then how can you figure out the derivative of the composite function? So for instance, how can we figure out the derivative of sine squared x, or of sine of x squared? Okay, and so these composite functions are going to arise all the time. So we're going to want to know a way of being able to take the derivative of it. Okay, questions before we move on? Okay, so let's talk about what the rule is. So roughly, what does the chain rule say? It says that the derivative of a composite function is the product of the derivatives of the two individual functions. But the actual statement's a little bit more subtle than this. So I'm going to say the theorem over here. So this is the chain rule. Okay, so the chain rule says, suppose that f and g are differentiable functions, and I'm just going to call their composition a name. So I'm going to call capital F of x, that's going to be equal to f of g of x. This is just giving it a name. I'm going to call it capital F. So then it turns out that capital F is differentiable, and we have this formula that what is the derivative of f prime of x? Well, it's this somewhat complicated formula, and I realize I made a typo there. So it's f prime of g of x times g prime of x. Okay, so it's like the derivative of g times the derivative of f, but being evaluated at g. So it's a little bit of a complicated formula. In particular, the formula is not simply that f prime of x equals little f prime of x times g prime of x. Okay, it's almost this, but instead of plugging in an x here, you've got to plug in a g of x. Okay, so this is maybe a little bit confusing before you see some examples. So we're going to do a number of examples of computing the chain rule. Okay, so I'm going to go to the next page, but I'm going to rewrite this formula, and we're going to do this in a couple of examples to see how it works. Okay, so example 1 is compute the derivatives of sine of x squared and sine squared of x. And let me just recall just the chain rule. If capital F of x equals little f of little g of x, then capital F prime of x is equal to f prime of g of x times g prime of x. Okay, this is the chain rule. Okay, so we're going to have two problems here. We've got sine of x squared, and here for number 2, we have sine squared of x. And maybe it's easier for us. Let's actually write that as sine of x squared. It's going to be better for this problem. Okay, so when you're first doing the chain rule, if you want to take the derivative of this, we have to recognize it as a composition, right? So if we recognize this as a composition, how do we do that? Well, this is f of g of x, where g of x is x squared, and f of x is sine of x. Right? This is what this, I haven't taken any derivatives yet. I'm just writing this as a composite function. What is the, how do you do sine of x squared? Well, if somebody gives you x, how do you evaluate sine of x squared? Well, first you square it, and then you take the sine. So that's f of g of x, or g of x is x squared. That's what you do first. You square it, and then you apply f to take the sine. Okay, so the chain rule says that the derivative, ddx, of sine of x squared should be equal to, well, in this case, it's f prime of x, sorry, f prime of g of x times g prime of x. And now let's write this down. So f prime is cosine, right? Derivative of sine is cosine. We remember this. So that's going to be cosine, but we don't just say cosine of x. What we actually do is we put cosine of g of x. So it's cosine of x squared. Right, where I'm going to label this, right? It's cosine. This thing here is g of x. This thing here is f prime of g of x. And then times the derivative of g of x. That part is simpler. That's just the derivative of x squared, which is just 2x. Okay, so this here is g prime of x. Okay, so this is the answer. So the derivative of sine of x squared is cosine of x squared times 2x. So you think of kind of like taking the derivative of the outside function and plugging in the inside function. So you might say, oh, derivative of sine of x squared is cosine of x squared. But it's not just that. You also have to multiply by this extra derivative, this extra g prime of x here in your function. Okay, so this is the answer for the first example. We'll go ahead and do the second example, but before we do that, do we have any questions about how this first example works? Okay, good. Okay. Oh, can I explain that again? Okay, sure. Yes. So
Oh, hello.
yes, Enoch.
Yeah. Sorry. I just my internet been giving hard time. You know, really the place I live in,
Mhm.
the area I live in, the internet can really give hard time. So Yeah, like for this one, I want to give my input also.
Sure.
Yeah, because you know that if you got the function to be equal to sine of x squared, that actually means that you have three different functions in there. You have the first function to be or f of x and is equal to another function which is sine of x. Then you have another function inside x again, which is the x squared. So you have to differentiate the outside and differentiate the inside part, which is you have to differentiate the x, the sine x, and differentiate the inside part, which is x squared.
Mm-hmm.
Yeah.
Exactly. And that's why we have this. We have the sine x and we have the x squared. Those are both the parts of this function. The differentiating the x squared is giving you the 2x, and the differentiating the sine x is giving you cosine x. But you don't just have cosine x, because it's not f prime of x, but it's f prime of g of x. So you have to plug in g of x to cosine of x. So you can't just have cosine of x squared. You have to have, you can't just have cosine of x. You have to actually have cosine of x squared. Okay, so maybe just to see this, I should write this. I can call this f of x, which is going to be equal to this f of g of x. And the key that you have to do here is you have to recognize what is your f and what is your g. What's your outside function and what's your inside function. And here the outside function is sine, that's your f, and the inside function is x squared. And once you know what f and g are, then you can just use this formula, that it's f prime of g of x times g prime of x. Okay, so if you just use this formula, that's what I have labeled over here. The cosine is f prime, the x squared is plugging in g of x, and then times the 2x, which is g prime of x. Okay. All right. Is that okay, Saley, or do you have more questions?
It's okay.
Okay, good. Okay. So let's do the other example. All right. So here we have, so if we have sine squared of x is going to be equal to f of x, which again, we'll write it as f of g of x. Now, what we saw here, right, is that the f and the g are now in the opposite order, right? You're first doing sine of x, that's the inside function, and then you're squaring it, right? So this is true where, in this case now, f of x is going to be x squared, and g of x is going to be sine of x, right? To do this, to do sine of x squared, you first do sine of x, and then you square it. So then the chain rule, right? So the chain rule says that capital F prime of x says that f prime of x is going to be equal to, well, we still have the same formula, f prime of g of x times g prime of x. And so I see James has sine of 2x. I think that's not quite right. That'll be part of the answer. So what is that going to be equal to? Well, f prime of, well, the derivative of x squared is 2x. But instead of just having 2x, you need to plug in g of x for x. So it's not going to be 2x, it's going to be 2 times sine x. Right? This is the f prime. This is f prime of g of x is 2 times sine x. And then you have to multiply by g prime of x. So we know that the derivative of sine is cosine. So this is going to be cosine of x. Oh, James, you're actually right. Okay, haha. So this, if you know the trig identity, this is actually the same thing as sine of 2x. So if you want to simplify this, then that works. So either of these examples is okay. Okay, so either of these answers is okay. This is just if you know the trig identity, 2 times sine x cosine x equals sine of 2x.
Hello.
And that works.
Hello.
Yes.
Darobos?
Hello, Enoch. Yes.
Yeah. Can we use the formula, or we can say the first principle to also find the derivative of sine x squared and sine square x also as well?
I mean, you could try to use the actual definition of the derivative, but the limit is going to be very hard to evaluate. So I don't think it's going to be easy to just do that limit and figure it out.
Oh, okay.
Yeah, I mean, in theory you can, but I don't know how to evaluate that limit.
Okay. Yeah, I can do it because if you see the function, there are two different functions there. The
Mhm.
one there is what you have is square on the angle, and which is the s square, and the next one is what you had the square on the sine itself, sine square x.
Mhm.
Yeah, so they are two different. The one that different. The next one is actually difficult, but it can be done. But the first one is so easy.
Okay, oh, so this first one is yes. I mean, I guess right. To do this with the definition of the derivative, if you could plug
Because
in x plus
if you
h
use the
for x.
definition,
Yeah. Yeah.
yeah, sure. If you are using the definition, you get sine the angle of x plus h
Mhm.
all square. Then you can share it out. Yeah.
Yeah. So I mean, let's see how this works. So maybe it would be okay. So if you take um, limit as h goes to 0 of sine of x plus h squared minus sine of x squared divided by h. Okay, so you can try to simplify this. So that's sine of um, x squared plus 2xh plus h squared minus sine of x squared divided by h. Um, I mean, I guess you can do this, but it doesn't seem that easy to do because you need to use some addition formula for sine over here. And I mean, it seems like it's going to be fairly complicated.
I don't think whether it can be even factor there. They are
Yeah, you
looking at
can't
it.
factor anything,
Yeah.
Um, but I mean, you can use addition formulas. You can use that this is sine of x squared times cosine of this plus cosine of x squared times sine of this. And I mean, again, maybe you can get it to work. I don't really want to take the time to go do this example. It's possible that you can get it to work, but I'd say it's not that easy, right? I mean, you can do it, but it takes a lot of work with trig identities and limits. So the point is, once you've already done the derivative of sine, then it becomes a little bit easier to just use the chain rule over here. Okay. Okay.
So
Are there other questions about these two examples?
Yeah, for an
Okay.
kick off.
Scholastica? Sorry. Okay. All right. Let's move on to the next example. Okay. So example 2. So if f of x is equal to x times the square root of x squared plus 5, then we want to compute f prime of 2. Okay. So for this, we need to recognize that this is going to use a couple of rules, right? So when we take a derivative, we see we have an x here, and we're multiplying it by this complex composite function, this square root of x squared plus 5. So
Yeah.
one second, Enoch. So the first thing is you have to realize that this is a product, right? Kind of at the highest level, this is a product. It's one function times another function, and then when and one of the parts of the product is a composition. Okay, Enoch, do you wanna start it off?
Yeah. I wanted to say something because like
Okay,
what you
sure.
were just saying, I wanted to say because
Yep.
you have the product of two functions. So
Mm-hmm.
you are actually going to use the product rule or the product law of derivative. Where, for example, if you are differentiating f of x against g of x or g of x, you will
Mm-hmm.
first of all differentiate f of x and hold g of x constant.
Mm-hmm.
Then next the next one is that you are going to hold g of x as a constant. You are going to hold f of x as a constant and differentiate g of x. So in this problem here, for example, to make it easier for yourself, you can say that, for example, you can say let your g of x, be equal to some value like x, and you have your h of x to be equal to the square root of x squared plus 5 now.
Yeah.
You
So
can
let
differentiate.
g of x equal, let me just repeat. So
Okay,
let g of
x
x
is
equals
equal to-
x and h of x equals square root of x squared plus 5.
Yeah, are we there? So yeah, so the next one is that if you differentiate,
Yeah.
okay, f from x. Now if you differentiate g of x, you get 1. And
Exactly.
you
So
hold h.
let me just recall the formula just because people maybe haven't seen the product rule in a while. So remember that f prime of x can be written as g prime of x times h of x plus g of x times h prime of x. This
Okay,
is
sure.
the so-called product rule. Okay, so this
Hello?
is recall that how we do a product. So this is our formula. You differentiate one and hold the other constant, and then you do the same thing in reverse. So okay, so proceed.
Yeah, so now we know that the first part is that if you differentiate g of x, you will have 1.
Hmm.
So you have 1 times pure h of x, and our pure h of x is the square root of x squared plus 5, which is 1 times the square root of x plus 5. You only get the square root of x squared plus 5. Then you do plus the addition root. Okay. Then you do plus. Now you are holding g of x constant, which is your only x. Then you differentiate h of x. And in a problem, if you differentiate h of x, the function there is in another form. You have to
Okay,
you
so
have to
hold on.
use
So let's great. That's perfect. Let me just slow down and write
okay, you
this.
have to use
Okay.
the power.
So what I'm writing here is so just sorry, 1 second. Right. So I just want to make sure everybody caught up, right? So we
Okay.
differentiate the x, that gives 1, then the h of x stays here. We have x squared plus 5, and then we add g of x, which is just going to be x, and then times
Yeah.
h prime of x, which we can't do right away because this is a composite function. So this is square root of x squared plus 5. Okay, and this is just so this is going to be a composition of two functions, right? So we're going to have to write down what that is and use the chain rule. So let me say this over here is going to involve the chain rule. Okay, so proceed.
Okay, so you can actually use a chain rule there.
Yeah.
So what you do now, after you have, if you differentiate that thing now, you only constant, then you do a derivative inside. So you have the derivative again of x squared plus 5. And we know that the derivative of x squared, you only have 2x, and the derivative of the constant, which is 5, goes to 0.
Mhm.
So you have that entire thing time. Okay.
Right. So we're going to write this
Okay.
as x squared plus 5 to the 1/2, right?
Yeah.
And so a lot of people are seeing the chain rule for the first time. So let's write down what exactly our composite function is, right? So we could have something, I'll use different letters. We have that I could write this as u of v of x, just because I don't want to use g again, because we already used g. Where in this case, this is equal to u of v of x, so what's going to be our v of x? So the v of x is the inside thing here, right? So that should be x squared plus 5. And our u of x is the outside function. So we take x squared plus 5, and then we're raising it to the 1/2. So u of x should be x to the 1/2, right? So for this, we're going to use the chain rule. So we remember here that the derivative for the chain rule is u prime of v of x times v prime of x. Okay, so Enoch, do you want to carry on? So what are we going to get here now when we apply the chain rule? Okay, well, okay, I'll do it then. So what is this? This is going to be equal to, well, u prime. U prime is x to the 1/2. We can use the power rule there. So it's going to be 1/2 times Well, it would normally be 1/2 times x to the minus 1/2, right? Because you're moving the 1/2 down and you subtract 1, so it becomes minus 1/2. But again, on the inside, you've got to put v of x. You can't just put x. So you're going to put x squared plus 5 here, to the minus 1/2. And then you have to multiply by v prime of x, which, as Enoch said, v of x is x squared plus 5, which means v prime is just 2x plus 0. So in this case, it's just going to be 2x. Okay, so this part of the product rule all comes over here. 1/2 times x squared plus 5 to the negative 1/2 times 2x.
Yes, yes, sure.
Yes, Enoch, okay, you're back. Okay, so let's just simplify it all. We have square root of x squared plus 5 plus, and now we have x times all of this. Well, here also we have a 1/2 and a 2, so we can cancel those out. And what we're left with is, what are we left with? We're left with x squared plus 5 to the negative 1/2, and then another x. So we could write that as x squared times x squared plus 5 to the negative 1/2. Okay? All right. So this is what we get if I just asked for f prime of x. But the question doesn't just ask for f prime of x. It asks for f prime of 2. So we need to punch in x equals 2 now, right? So f prime of 2 is now the square root of 2 squared plus 5 plus 2 squared times 2 squared plus 5 to the minus 1/2. And so what is that? Well, 2 squared plus 5, right, this is just equal to 9. So the square root of 9 is going to be equal to 3. So we're going to get 3 plus, well, here's 2 squared, that's 4, times, well, I'm going to get 9 to the minus 1/2. So what is 9 to the minus 1/2? Okay. So we have 3 plus, so when we punch in 2, we get 3 plus 4 times 9 to the minus 1/2. So remember, what's 9 to the minus 1/2, right? 9 to the minus 1/2 equals 1 over 9 to the 1/2, which is the same thing as 1 over square root of 9, which is the same thing as 1/3. So remember that there. So we end up getting 3 plus 4 times 1/3. And so if you simplify this, this ends up coming out to be 13/3. Okay, so that's the answer here. Okay, so it's a multi-step problem, right? I give you a function and I want you to calculate the derivative at a certain point. So first you have to recognize that the function is a product. So you're going to use the product rule. It's a product of two pieces, x and square root of x squared plus 5. So you go and you start to do the product rule. But as you're doing, right, so as you do the product rule, then this part's easy, and this part's easy, and this part's easy. But then you have one further part where in order to do this h prime of x, you now need to use the chain rule. And to use the chain rule, you have to recognize square root of x squared plus 5 as a composition of two functions. First, you do x squared plus 5, and then you take the square root. And so writing that out formally, you've got v of x is x squared plus 5, and u of x is square root of x, or x to the 1/2, same thing. And then you can use the chain rule to get this formula for the derivative. When you write it all out together, you end up with f prime being equal to this expression. And then since the problem asks you to do f prime of 2, not just f prime of x, then you need to punch in 2 and actually figure out what this equals to. And in the end, it equals to 13/3. Okay, are there any questions about any step here? Some of the main part that we're interested in is the chain rule, but here the chain rule is kind of just one intermediate step in the middle of a more complicated problem. Yeah, 3 plus 4 times 1/3. Oh, sorry. Oh, plus. Yes, sorry. Thank you. Yeah, plus. Yeah. Any other questions on this? Okay. So these are a couple of examples of the chain rule. Okay. So maybe I should say a little bit. So this is a typo. It's section 2.5. So why does the chain rule work, right? I mean, I gave you this formula out of nowhere. So if you want to read a full proof, you can read it in the textbook. It's on page 119, and you can do a full proof of this. So I'm not going to give a full proof, but I want to tell you a little bit about why the chain rule should be true. Like, why does it make some sense? So remember that if you have a differentiable function, what does the derivative mean? Derivative means a rate of change. This is why calculus has applications, because calculus is about how things change. So it's saying that the derivative is an approximate rate of change. So if f prime of x is some value, m, then a small change in x should result in about m times as big a change in f of x, right? This is the whole, tangent line thing, right? If we have, if this is y equals f of x, and I have, x over here, and then I make some small change here, delta x, then this should increase about, the tangent line is giving you an approximation to how this is going to increase. So if this is delta x, then this over here should be m times delta x, if this right triangle is delta x. And so what we see is that if this is delta x, so the change in f, right, is about, not exactly, but it's about, m, which is the derivative, times the change in x. Right, this is what we call delta x. Okay, so every time we move over by delta x, we move up by that amount times m, because the slope is exactly the rise over the run. So if you run as a certain amount, then your rise is you have to multiply by the slope. This is what a slope is. Okay. So you make a little change, then a little change in the input, then the output should change by about m times as much. This is what a derivative is. Okay. So how does this affect the chain rule? So now let's say that we have f prime of x, and that's going to be, and let's say it's a composition. So it's f of g of x. So let's say that we make a small change in x. So like we replace x with x plus h. What change does this lead to in g of x? And then what is the resulting change in f of g of x? Well, the idea is what we should have is that g of x plus h should approximately be, well, it should be g of x plus, well, you're making a small change h, so the function g should change by its derivative times that much. So it should be g prime of x times h. Okay, right? This is, over here, what is g of x plus h? You should think of this as the starting value. And this is the derivative. And this is the input change. Okay, so you have your starting value, your derivative, and your input change. And the final value should go up by about the input change times the derivative. That's what a derivative is. So now what do we have? So now, well, f of g of x plus h, well, if g of x plus h is about this, then I should be able to punch that in for g of x plus h. So this is about f of g of x plus g prime of x h. And the idea is if h is small, then this g prime of x h is still small. Oh, sorry, can you not hear me? Can people hear me? Are other people getting me? Alexander said he's not getting me. Are other people getting me?
Yes,
You
we are
are. Okay.
getting.
Okay, so I think it must be a problem on your end, Alexander. Something with your microphone or with your speakers. Okay, so in any case, I'll keep going. So this is still small. And so what is it? Well, here we have f of g of x, but now you're making a small change in g of x. So this should be roughly equal to, well, f of g of x plus, again, we're just going to have the derivative times the input change. So it's just the derivative of f, but what we're plugging in to f is g of x, not f. So this is what we have is going to be the derivative of f at g of x at this point. So we have f of g of x and then times the input change. And the input change here is g prime of x h. Right? So this over here is the input change. And this over here is the derivative. And this over here is the starting value. Okay, so this argument says that if you make a small change in the input to a composite function, you get a kind of intermediate change by the input times g prime of x, and then a total change by the input times g prime of x times f prime of g of x. And so what this tells us, so the upshot is that small change h in input to f of g of x gives a change of about f prime of g of x times g prime of x times h in output. Okay. And what that tells us is exactly, well, so then what's the rate of change? If you make a change of h in the input and you get this whole change something times h in the output, then the derivative is exactly the scaling factor. So this thing here is the derivative of f of g of x. Okay, so this is basically the reason the chain rule works. This is not a proof. It's a little wishy-washy. If you want an actual proof, you can read it on page 119 of the book. Okay? But this is the main reason why the chain rule works. Basically, you can think of it as if you make a small change in x, that gets magnified by a factor of g prime of x in terms of what kind of change it creates in g, and then that gets further magnified by a factor of f prime of g of x in terms of what kind of change it makes in f of g. So each function throws on a new magnifying factor. And the first factor is g prime of x, and the second factor is f prime of g of x. And you put those two factors together, you get the entire magnifying factor, a magnifying of change. And that's really what a derivative is. It's a factor that magnifies the change in the input to give you the change in the output. Okay, that's what a slope or a derivative is. Okay, so this is a little intuition for why the chain rule works. But it's not a full proof. If you really want to see a proof, then you've got to go read it in the book. Okay, any questions? Okay. All right. So enough about why that works. So and for the rest of today, I want to talk about an application of the chain rule. So this is called related rates. It's going to be an application of the chain rule. So I want to first, talk a little bit about um, what what another way of thinking about the chain rule. So I want to think about the chain rule where our main variable is time rather than x. So I'm going to call it t instead of x. So one way of thinking about the chain rule is that if we let u be g of t and capital F is a function of u, so we can write that. So we can write basically, that the what's the derivative of f with respect to t. So it's the derivative of f with respect to u versus times the derivative of u with respect to t. Basically, the way we're thinking about this is that if f uh, is equal to f of u, uh, and if that's also what do I want to say? Um, how do I want to put this? Let me just think here. Let me erase this. Um, so this over here basically, yeah, so this over here, this du dt is the g prime of t over here, and this df du, this is really going to be f prime of u, which is maybe I'll write this f as a function f of, sorry, and f is a function f of u, then this is how we can do it. So this is f prime of u times g prime of t, or in other words, this is f prime of g of t times g prime of t. Okay, so this is just another way of writing the chain rule. You'll see this in the textbook chapter, that df dt is equal to df du times du dt. This is a way of writing it. And just to make this a little bit clearer, to think about this in the context of an example that we've already done. So if we look at sine of t squared instead of sine of x squared, we know that the derivative of, with respect to t, of sine of t squared, well, we figured this out already. This is cosine of t squared times 2t. So if we let u equals t squared, and we let, yeah, maybe I'll write this as little f of u. Okay. So if we let u equals t squared and we let f of u be sine of u, then the composite function is sine of t squared, then the chain rule gives us exactly this derivative of f with respect to u, so that's cosine of u, and then times derivative of u with respect to t, that's 2t, and when you put it all together, you get cosine of t squared times 2t. Okay, so we're not doing anything new. This is exactly the same way we've done the chain rule before, but the idea is that if a function depends on a variable that itself depends on time, then to take the derivative of that function with respect to time, you take the derivative of the function with respect to the variable, that's this cosine of u, and then you take the derivative of the variable with respect to time. So that's du dt, that gives you this 2t, and you put them all together. And then if you want to write the entire thing in terms of time, then instead of writing a u here, you write a t squared. So you get cosine of t squared times 2t. Okay? So that's this is just another way of writing the chain rule. If it's a little confusing, don't worry about it. It's going to make much more sense when we do the examples. Okay? So let me try to do this in the context of an example. So let's say we have the following problem. So air is being pumped into a spherical balloon at a rate of 100 cubic centimeters per second. So we want to know, how fast is the balloon's radius changing when the radius is 25 centimeters? Okay, so a bit of a confusing problem if you haven't seen something like this before. By the way, this is all under the name of what's called related rates. And this is in section 2.7 of the book. Okay. So the first thing you have to do to write a problem like that, so step one, you have to write down an equation relating the quantities. The quantities. So here we have a volume, right? We've got a volume And then we've also got a radius. So we need a general equation that relates the volume and the radius of a sphere. And so if you remember from geometry, the equation in this case is that the volume is equal to 4/3 times the radius cubed. Okay, this is the equation for the volume of a sphere. Okay. So what you do for step 2 of a related rates problem is you take the derivative of both sides with respect to time, with respect to t. So what happens here? So the idea is we think of all of these things as the volume is a function of time and the radius is also a function of time, right? So the volume, because the volume is changing with time and the radius is changing with time. Okay? So the derivative of the volume with respect to t is just dv dt, right? That's what the rate of change with respect to time is just the derivative. What about this other side? Well, what I should really be thinking, and I'm going to write it in another color, is I should really be thinking that this radius is really a function of time. So I'm going to write it as r of t instead of just r. And so now to take the derivative of this side using we have to use the chain rule because you've got an inside function r of t and you've got an outside function which is 4/3 times blank cubed. Right? So if I give a little aside here, this is basically f of r of t with, r of t just being r of t. We don't know what it is. And f of u being equal to 4/3 u cubed. Right? Because what is this volume? What is this function? It's you first take the radius and then you cube it and multiply by 4/3. So in this sense, it's a composite function. First take the radius as a function of time, and then to get volume, cube the radius and multiply by 4/3. So to use the chain rule, so the chain rule says that the derivative is f prime of u times r prime of t, or in other words, f prime of r of t times r prime of t. Okay, so in this case, this would be 4/3 u cubed. You bring down the 3, that's going to make it 4, and you subtract 1, that's going to make it 2. So this is going to be 4 times u squared, and then times r prime of t. So, and in this case, this is just r. So u in this case is just equal to r, right? So maybe I should just call this r instead of u. Let me just call it r. F prime of r times r of t, and this we're going to be r. So the upshot is what you get when you take this derivative, thinking of it using the chain rule, is you're going to get 4 times r squared, and then times this extra r prime of t, or we can write it dr dt. Okay, so what you're really doing here is taking derivative with respect to r, and then multiplying by dr dt. Okay, this comes from the chain rule. And so now we can actually answer the question, how fast is the balloon's radius changing when the radius is 25 centimeters? Well, here our radius would be 25 centimeters. And we know that the volume is changing at 100 cubic centimeters per second. So this is, 100 centimeters cubed per second. It's really 100. So what we end up with as an equation is we get, 100 equals 4 times 25 squared times dr dt. Then it turns out the 100 will cancel with a 4 and 1 factor of the 25. And so what we're left with is that we have 1 is equal to 25 times dr dt, or dr dt equals 1/25th. And since it's a rate of change of radius, that's going to be 1/25th centimeters per second. Okay, so to do these, so that means that even though the volume is changing, it seems pretty fast, 100 cubic centimeters per second, the radius is actually increasing very slowly. It's increasing only at 1/25th of a centimeter per second. And that's probably good, because if the radius increases too fast, then maybe you're going to pop the balloon. Okay, so this tells us that if you have a pump which is pumping a certain amount of air that you can measure, then you can understand how that's going to translate into how the radius changes. Okay, so to review this, what do you have to do? You first write down an equation relating the quantities. So here's an equation that relates V and R. V equals 4/3 R cubed. And then you take the derivative of both sides with respect to t. The V just becomes dV dt. The 4/3 R cubed, you just take the derivative in the normal way. It's just 4R squared. But then because of the chain rule, you have this extra R of t in here. So you have to throw in an extra derivative, dr dt, that you multiply by. Okay. And once you have that, then you can plug in all of the values and solve for the quantity that you actually want, which is this dr dt. Okay. And when you do that, and when you solve everything, you end up getting that dr dt is 1/25th of a centimeter per second. So any questions on this? We'll do a few more examples so you can see how these work. Okay, let's do another example so we can get fluent in this. So a boat is pulled into a dock by a rope that is attached to the front of the boat and passing through a pulley on the dock that is 1 meter higher than the boat. If the rope is pulled in at the rate of 1 meter per second, how fast is the boat approaching the dock when it is 8 meters from the dock? Okay, so this is complicated. So for a problem like this, we're going to start with a step 0, which is draw a picture. All right, we should definitely draw a picture of what's going on. So here's the boat. Here's the boat. And here's the dock. And here's the pulley. And we have that this dock is 1 meter. The pulley is 1 meter above the level of the boat. Right, here's the water. Right, there's the water. And so what I'm going to do is I'm going to draw a right triangle here. It's going to be a right triangle. And we know that the rope is getting pulled at the rate of 1 meter per second. So let me actually label these two quantities. I'll call them A and I'll call them C. So this is a picture. And the point of the related rates problem is that the problem is giving you some information about how C is changing, right? I mean, what we have is that dc dt, so the rate of change of C with respect to t, the rope is being pulled at a rate of 1 meter per second. So dc dt is 1. But what the question is asking is, what is dA dt at t equals 8, right? This is the question. Sorry, so not what is dA dt. What is dA dt when A equals 8? Maybe I'll just write it out in words. So what is dA dt when A equals 8? Right, that's what this question is saying. It's saying if C is decreasing by 1 meter per second, because that's how fast the rope is being pulled, then how fast is the boat getting close to the dock? So you're given dc dt, and you want to know dA dt. Okay? So now step 1, which is what we have before, we need to write an equation relating the quantities. Okay? And so what equation are we going to be using here? Well, we're going to use the Pythagorean theorem, right? Because we have a right triangle, right? So the equation is going to be a squared plus 1 squared is equal to c squared, right? That's our equation that relates a to c. This is why it's called a related rate. A and c are related, and we want to know how a rate on one of them compares to a rate on the other one. And so step 2 is differentiate both sides with respect to t, with respect to time. And so what our key that we remember is every time we take a derivative of one of these quantities, you have to multiply by d of that quantity dt. This is what comes from the chain rule. So what we get here is for a squared, we get 2a, but 2a times dA dt, then plus 1 squared, that's just a constant. So the derivative is just 0. And that's going to be equal to 2c dc dt. So this is what you get when you differentiate both sides with respect to t. You differentiate both sides normally, but every time you take a derivative of a variable, you've got to throw in dA dt or dc dt in that case. So I should really say step 3 is to punch in values. Right, so the question says, how fast is the boat approaching the dock when it's 8 meters from the dock? So when we're what we care about, this a is going to be equal to 8. Right, so we're going to punch in 8 for a. We know that dc dt is 1 meter per second. This is given to us, right? So this is 1. And then we need to know c, but c we can figure out from the Pythagorean theorem, right? Because we know that we have this equation over here, right? So we know that 8 squared plus 1 squared is equal to c squared, and this is going to give us that c is equal to square root of 65, right? Because c squared is going to be 64 plus 1. So that means over here, we're going to get a square root of 65. So what does the equation become? It becomes 8 times dA dt, or sorry, 16, 2 times 8 times dA dt equals 2 times square root of 65 times 1. And if you solve this for dA dt, well, you can cross out the 2's from both sides, and what you're left with is dA dt is going to be equal to square root of 65 over 8, and then this is a speed, so the unit is going to be meters per second. Okay. All right, so this is how this problem works. It sounds complicated when you write it down, but when you actually do the mathematics, it's not so bad, right? You just draw a picture of your situation, you write down an equation relating the quantities, and then you differentiate both sides with respect to t. And the point is, once you do that, once you differentiate both sides with respect to t, you have all of the information you need to solve for the quantity you want. So you want dA dt, you need to know what's a, what's c, and what's dc dt. But these things are all basically given to you. A is 8. That's from the diagram. The boat is 8 meters from the dock. dc dt is 1 because the rope is being pulled at 1 meter per second. So it's shortening this at 1 meter per second. And then c you have to figure out using the Pythagorean theorem. But that's okay. Once you know a, then you can figure out c. Okay, so you get this nice result. And what this is saying is that as the rope gets pulled at 1 meter per second, the boat is actually getting pulled in a little bit faster than that. You know, this is root 65 over 8 is a little bit more than 1. So the boat actually gets pulled in faster than you pull the pulley. That's one of the advantages of, having an elevated pulley. Okay, it's efficient in terms of pulling things in. Okay. All right. Any questions on this? Okay, let's do one last example, and then we'll finish. So last example, example 3. Two cars start moving from the same point. One travels south at 60 miles an hour, the other travels west at 25 miles an hour. At what rate is the distance between them changing after 2 hours? Okay. Okay, so let's, again, step 0, we're going to draw the picture. So maybe I'll start the point over here. One car is traveling south, and the other car is traveling west, right? So this is car A, and this is car B. And car A is 60 miles an hour. Okay, that's it. And so this is, it's going to, again, form a right triangle because of how they're being drawn. Okay. So,
Yeah,
yes,
that
question?
open?
Yes, Enoch?
Yeah, so this one is actually talking about vector, right? It will be a vector in 2 dimensions.
Yeah, but we don't have to use vectors to do this. We can do it with vectors, but we don't have to.
Oh,
Like we can
okay.
do this with just one variable in Pythagorean theorem. So just because this is a new concept, yeah, maybe we won't use vectors because that'll keep the related rates clearer. Okay, so let's give these distances maybe names. I'll call this I'll call this distance A and I'll call this distance B. Okay. So, and then maybe this distance is C. This is what we want to know. Right, so step 1 is write an equation. Write equation relating the quantities. The quantities. Right? So again, this is just going to be the same thing that we had before, right? It's still just going to be a squared plus b squared equals c squared. It's just the Pythagorean theorem still. So step 2 is differentiate both sides with respect to t. So here we just do a standard derivative. So the derivative of a squared is going to be 2a, but then an extra dA dt from the chain rule. The derivative of b squared is 2b with an extra dB dt from the chain rule. And that's equal to the derivative of c squared, which is going to be 2c times an extra dc dt from the chain rule. And since we have all these 2's, if we want, we could just cancel out all the 2's right now. Okay. And remember, what is the quantity that we want? Well, the quantity that we want is this, dc dt, right? Because c is equal to the distance between the cars, right? So c equals the distance between cars. Okay. So the quantity that we want, so step 3, well, we want dc dt, right? So we have to punch in values for everything else. Okay. Well, okay, so a few of these things are easy, right? We said car B is traveling west at 25 miles an hour. That means dB dt equals 25. That's the rate. It's a constant rate of change because it's at a constant speed. So this here, this dB dt is 25. Likewise, car A is traveling south at 60 miles an hour. So the change in A with respect to t, that's a constant rate of change. That's going to be 60, right? I mean, you just have A is going to be 60t, right? I mean, in particular, what you really have is that A is equal to 60t and B is equal to 25t. Right? That's what it means to travel at a constant rate. It's just rate times time. Okay? So now, so this tells us, of course, dA dt equals 60, dB dt equals 25. And what about A and B themselves? Well, we have after 2 hours, right? So in our problem, we have t equals 2. And so since t equals 2, you get that A is equal to 60 times 2 is 120, and B is equal to 25 times 2 is equal to 50. So for A, we're going to use 50. Sorry, let me do it in green. So for A, we're going to use 120, and for B, we're going to use 50. And then lastly, we have C, which we can figure out with the Pythagorean theorem. C squared. So since C squared is equal to A squared plus B squared, we have that C squared is equal to 120 squared plus 50 squared. And it turns out that this is equal to 16,900, and this gives us that C is equal to 130. Okay? So this C here is going to be 130. Okay. And so what we're left with is the equation that we want to solve. So we get 120 times 60 plus 50 times 25 is equal to 130 times dc dt. And let me just use a calculator to solve this. So what is it? 120 times 60 plus 50 times 25, that's 8450. And if I divide that by 130, that's going to turn out to be 65. Okay? So if you end up solving this, this actually becomes, you end up getting that dc dt equals 65, which is the rate. And again, it's a rate, so it's going to be miles per hour. Okay? So again, it's the same setup as all of these related rates. You draw a picture if the picture is helpful. Then you write an equation relating the quantities. You differentiate both sides with respect to t. This is where the real work is. This is where you're actually getting these related rates, where you're showing how the rate of change of one quantity is related to the rate of change of the other quantities. And then you find what is the thing that you're actually solving for, and can you then punch in values for everything else? So in this case, by using the information in the problem, we could punch in A equals 120, dA dt equals 60, B equals 50, dB dt equals 25, C equals 130, had to use Pythagorean theorem for that, and then dc dt is the unknown. This is what the problem's asking for, what you're trying to solve for. But once you do that all, then you just solve for dc dt, and you end up that, this over here is going to be equal to, this is 8450, if you want. This is 8,450. And if you divide that by 13, you end up getting 65. So all of these related rates problems follow the same template. And to me, it's like kind of amazing that, using this calculus, you can see how the way one thing changes affects how something else changes. And a problem like this, you can imagine being very important for something like air traffic control. You want to know how close helicopters are to each other or how class planes are to each other, and they're traveling in different directions in different, at different rates, and you need to make sure that they stay a certain distance away from each other, so you don't want them to get too close. And this kind of thing can model, how you can understand this using radar. So actually, one of the problems on the homework is about this. So let me say for homework exercises, so the first one is just going to be a straightforward derivative. So compute the derivative of 4x minus x squared to the 100. This is just an exercise in using the chain rule. Okay. Second problem is a little bit more involved. So you have a model for the length of daylight in hours in Philadelphia on the teeth day of the year is given by this. So L of t is equal to 12 plus 2.8 times sine of 2 pi over 365 times t minus 80. So this is a function where if you plug in t, so like the teeth day of the year, meaning like t equals 1 corresponds to January 1st, t equals 2 corresponds to January 2nd, etc. So if you plug that value in, then you'll get roughly how many hours of daylight there are in Philadelphia that day. And so compute the rate of change of the number of daylight hours per day on March 21st and on May 21st. So this is a derivative, right? It's a rate of change. That means derivative. So you're going to compute the derivative of this on March 21st and May 21st. So you have to figure out what day of the year those are. And then the question is so this is going to end up being a chain rule problem. Going to take a little bit of work to do the chain rule. And then on which day is the number of daylight hours per day increasing faster? So on March 21st, are there going to be more daylight hours? Is the amount that the daylight hours are increasing per day, is that faster or is it slower than on May 21st? Okay, so which time of year is the sun starting to shine longer and longer at a faster rate? So this is question number 2. And then chapter 3 is a related rates. So a plane flying horizontally at an altitude of 1 mile and a speed of 500 miles per hour passes directly over a radar station. Find the rate at which the distance from the plane to the station is increasing when the plane is 2 miles away from the station. And so maybe I'll start you off just with your diagram here. Right, here's your radar station. Your plane is flying straight over. This is your plane. And then the plane at some point over here is 2 miles from the radar station. And the plane is flying at an altitude of 1 mile. So this is 1 mile. And you want to know if the plane is going at 500 miles an hour, then how fast is the distance from the radar station increasing? Okay, so it's flying 2 miles away from the station, and then how fast is that going to increase? Okay, so that's a related rates problem to try for homework before our next class. Okay. Now we have lots and lots of time until the next class. So the next 2 weeks, unfortunately, there's not going to be any class because I have conflicts on both of those Thursdays. So the next time that we're going to resume is March 13th, and we'll discuss linear approximation, Newton's method, and L'Hopital's rule. But so this is 3 weeks from today, which means lots of time to try the homework. All right, so I'd like to see, a number of people try out these homework problems and try to find solutions, or if you get stuck, to ask the other people in the group for help. Because I think you have hopefully enough time over the next 3 weeks to really put some effort into these questions so that we can discuss them next time. Okay, so as always, thank you for your attention, and I'm sorry that it'll be a little while until we see each other again, but I'm looking forward to resuming on March 13th. All right, any questions? I'll stop the recording.